coefficient r, and then you can also test to see if the correlation coefficient is significant or not. Okay, so once we have done that, I should have left those data points up. We can find the best fit line. This is where we have linear regression. Okay. Best fit line. Okay. So linear regression is sometimes also called ordinary least squares regression. Okay. Okay. So the question is, how do we know what the best fit line is? So let's say these are my 4 data points. Okay. So we will still use the data points 1, 2, 3, 4, and 2, 6, 4, 8 as my x and my y. So we will still use these. And so if I say, well, what do you think the best fit line is? Someone might say it's this line. Okay, that's a straight line. Right. That seems reasonable. Somebody else might say, no, not that one. This one. That's a better line. You go, maybe, I guess. So it's hard to say, right? How do we know what the best fit line is? Okay, which line is better? Who thinks this one's better? Who thinks this one's better? Okay, so it seems like this one's better, right? Right? Well, the idea behind least squares regression, okay, well, we get the idea of ordinary least squares regression is we're trying to minimize what we call the squares of the residuals. Okay? We want to minimize squares residuals. Let me just do something very quick. We've got all sorts of different ones. Okay, we want to minimize the squares of residuals. Let me actually get a slightly different line here. This one went through 2. I actually wanted to go through 1. Okay. Well, we could have all sorts of lines, and then it's like which line is the best? Which line is the best? Okay. So let me talk about a residual first. The residual, also called E, we saw this in ANOVA. The residual is the difference between what our model predicts and the actual data point. Okay, it's the difference between the actual minus what's predicted. So in ANOVA, the residual was the within group variation. It was the difference between each individual lamb and the group mean. Okay, because under that model, the model predicts, if you're in group 1, we would predict you to have this value, which is the group mean. But of course, not every individual has that same value, so that would be a residual. In linear regression, the prediction is defined by the line, the prediction line. Okay, and so the actual data point is your y value, and the predicted data point is your y hat. Okay, so let's say we have two candidate lines here. Okay, so let's say our two candidate lines is this one that goes through the two endpoints, which seems like a pretty good line. And then another one, which I've got right there. Okay. So do you remember how to write equations of lines, or how to get equations of lines based on 2 points? Alright, so over here, so we have candidate 1. Actually, this one's easy. It's y equals 2x. Alright? Y equals 2x, that's candidate 1. And then candidate 2 is y equals, it's going to be 1.6x plus 1. That was, I took an aside to get this. Alright, so under candidate 1, let's do the predictions. Okay, so I have x and I have y. Alright, so this is candidate 1, y hat. These are the predictions under candidate line number 1. So under candidate line number 1, I would predict my y to be 2. For the number 2, I would predict the y to be 4. For this, I would predict it to be 6, and for here, I would predict it to be 8. Okay, so my residuals under candidate 1 is 0. Over here, it's 2. Over here, it's negative 2. And over here, it's 0. The actual minus the predicted. Okay? So the total sum of squares residuals, we want to minimize the squares of the residuals. So the sum of squares residuals would equal 0 plus 4 plus 4 plus 0. I would have a total of 8. This is my sum of squares residuals for candidate 1. See that? So, total sum of squares residuals equal 8. Is that okay? So, under candidate 2, let me, we gotta figure out. I still want to get that up there. So my y hat for line 2 and my residual for line 2. Okay, so I plug in 1 for x, and I get 1.6 plus 1, I would predict 2.6. And then I plug in 2. 2 times 1.6 is 3.2 plus 1, I get 4.2. I plug in 3, and I get 4.8 plus 1, 5.8. And I plug in 4, and I get 6.4 plus 1, 7.4. So the difference here is the actual minus the predicted, so I get negative 0.6, I get positive 1.8, negative 1.8, and 0.6. Okay, so negative 0.6 squared. So if I square the residuals, so sum of squares residuals will equal 0.6 squared, 0.36, plus 1.8 squared, I don't know what that is, 3.24? 3.2. Yeah, 3.24. Plus 3.24 plus 0.36. Alright, so I get a total of 7.2. So my sum of squares residuals here total sum of squares residuals (7.2). Is that okay? Alright, so if we're comparing candidate 1 with candidate 2, candidate 2 has a smaller sum of squares residual, so this is going to be a better line than this. Okay? It seems, when you draw the picture, it seems like this would be a good line, but it turns out that just angling it slightly reduces our residuals even further. And this is our criteria for picking the best fit line is the one with the that minimizes the squares of the residuals. Okay, for ordinary least squares regression. All right, and well, I knew the answer going in, and this is going to be 7.2 is the smallest sum of squares residuals that you can get with any single straight line. So if you were going to draw a single straight line through any data, through these 4 points, the minimum sum of squares residuals that you could possibly get would be 7.2. You're not going to find another straight line that provides a smaller residual.
How did you know that?
How did I know that? Okay, we'll get to that. Okay. All right, but this is the concept of picking the best fit line. Okay, because we're trying to get the line that minimizes the sum of squares residuals. Okay, and so the residual is the difference. So is the difference between the actual line and the actual data point and the predicted point. So for line 1, there's no residual here, but then there's a difference of 2 and a difference of negative 2. Okay, and then we square those. So I guess we have a square there and a square there. With the other line, okay, this one. So with my other line, we have a residual for all of the data points, but then apparently when you square them, the total sum of squares is smaller. Okay. Sum of squares residuals.
Why does it have to be squared and not just like the absolute value of the difference?
That's a good question. There is another branch of statistics that does the absolute value of the thing, and that ends up being more closely related to medians rather than means. Technically, the mean is the point that minimizes the square distance from all other points, or the I'm sorry, what did I say? The mean is the point that minimizes the square distance from all other points, and the median is the one that minimizes the absolute value difference from all other points. Okay, so why is a tough question. it has some nicer properties, I guess, and puts a little bit more emphasis on outliers, or like outliers will penalize ordinary least squares regression a little bit more heavily than what you might be suggesting, which I don't know the name of, but it's not entirely wrong to go that route. It's just not so commonly done.
Yeah.
Yeah.
Sorry, can you go over how you got the numbers for the sum of squares residuals again, the 0.36 and 3.
Oh, okay. So, are you okay with how I got the
Yeah.
2.6 and the 0.6?
Yeah.
So all I did was I'm doing the e squared. So I'm doing 0.6, negative 0.6 squared gives me
Okay.
0.36, and 1.8 squared gives me 3.24. Negative 1.8 squared gives me 3.24, and 0.6 gives me 0.36. Okay. Yeah. Sorry.
No, it's okay.
Yeah. So that's why we call it the sum of squares. I'm spitting. Sum of squares residuals. Okay. Yes.
Just want to make a remark that after so many years of schooling, this is the first time ever that someone actually drew like a square on the graph.
Oh.
Literally, I see this for the first time. I'm just so wowed by it.
Okay.
Thank you.
Well, there you go. Yeah. This vertical distance is the residual. It's the difference between, right? For the data point 2, the actual point is at 6, but according to the line, we predict it to be 4.2. Okay. So this vertical distance of 1.8 is the residual, and then we square it, okay? And then we do that for all data points. Yeah, maybe they don't do it because, well, with 4 data points, it's easy to see, but in regular regression, you probably have like 50 points, and you wouldn't want, you can't draw 50 boxes, and I mean, you can do it with a computer, but it looks like a mess. So, but this is what we have. Okay. All right, so that is how or the concept of the best fit line, okay? So how did I know that this was going to be the best fit line? Okay. So I'm going to skip the whole derivation and stuff. It's calculus, okay? You use calculus, and you're trying to minimize this function, okay, of sum of squares residuals. You can figure it out. You just say, you know, whatever line I put in here, you know, y equals mx plus b. Whatever line that is, I take the difference between the actual data points and the predicted thing, and I'm trying to minimize this. You know, you use calculus to minimize that. Anyway, smart people did that for us, and they came down with this formula that works for all linear regression cases. Okay, so the best fit line. So your linear regression line y hat, our prediction for y. Let me just check the notation. The notation is always different in every book. B0 plus B1x. Okay. Yes, that's right. Okay. So our linear regression line, B0 plus B1x, this is going to be our intercept. And this is our slope. We'll always have these properties, okay? The slope, you find the slope first, is going to be r times the standard deviation of y divided by the standard deviation of x. And B0 is going to be y bar minus B1 x bar. Okay. The linear regression line will always pass through the point x bar, y bar. It will pass through the mean of x and the mean of y. So when I had the data points 1, 2, 3, 4, 2, 6, 4, 8, x and y, right? My x bar was 2.5, and my y bar was 5. My standard deviation of x was 1.291, and the standard deviation of y was 2.582, and my correlation was 0.8. Okay, I used these 5 numbers, and I just plugged them into here and here, and that's how I got y hat is equal to 1.6x plus 1. Okay, so the slope, if I plug in these numbers, for the slope b1, I would plug in 0.8 times 2.582 over 1.291. I get a slope of 1.6. And then plugging that into my b0, I have y bar, which is 5, minus 1.6 times 2.5, and I get 1.6. Wait, did I do that right? Alright, I'm sorry. 1. I get 1. Not 1.6. I get 1. Just reading it back. Okay. So my overall, so plugging these values in, I get y hat is equal to 1 plus 1.6x. Okay, and so this is the work of other people. They just said, if you want to minimize the squares of the residuals, do this, and you will get this line which minimizes the squares of the residuals. Okay. Let me just talk a little bit about the interpretation of the slope and the intercept. Okay. So over there, my slope is 1.6. In algebra, they teach you the slope is rise over run, which is correct, but not quite so meaningful. Okay. In this problem, in this context, we have no meaning. X and y are just dummy variables. I didn't actually associate them with any actual thing. But the definition of the slope is how much we expect y to change when x changes by 1. Okay, so the slope is how much we expect y to change when an x changes by 1. Okay? Or, and the key is the word expect, okay? Or if you don't want to use expect, you can say how much we predict. So expect or predict, those are the key words, because y doesn't necessarily change by that much when x changes, okay? When we go from 1 to 2, x changes by 1 from 1 to 2, we're expecting the y to change by 1.6. But in reality, it didn't change by that much, okay? So it's just how much we're predicting y to change or how much we're expecting y to change but it's important that we say we predict or we expect because it may or may not necessarily do that. So maybe it'll be more meaningful in another context where we have actual things associated with x and y. And the intercept is 1, is b0, which is equal to 1. This is our prediction for y. If we plug, if x has the value 0. Okay. Sometimes it does not make sense for x to have the value 0, but so then the intercept would not have a meaningful interpretation. But sometimes it's okay to have x to be 0. So for example, maybe we are looking at I don't know, a certain model of car. Let's say a Honda Civic. And we just get we go on Craigslist, okay, or we go to dealer websites, and we just see, how much is this car selling for? How much are they selling a Honda Civic based on how old is the car? Okay, so maybe at 0 years, it sells for how much is a new Civic? 20 grand, something around
Probably
there.
at 14,000.
14? No, that's like
No,
a
like
Nissan
18,
Versa.
19.
Huh? 19,000, 18,000, whatever. Okay, so we will say 19,000. Yeah, cars are expensive, and
Yep.
and then okay, so let's say we find I don't know, a 2-year-old car, and it's right here in value, and then
Not a Civic.
4-year-old car, it's right there, and I don't know how far this scale goes. Okay, so maybe it hardly drops in value, or is that whatever? Okay. So let's say it looks like this, and then we fit, and you find multiple cars at different points, and some are worth more, and some are worth less, and things like that. But anyway, you fit a linear regression line. Okay, so you find multiple cars that are worth that are 4 years old, and some are worth more, and some are worth less. Okay, of course, there's a multitude of factors that go into determining the price of a car, where age is one of them. And so let's say y hat being price is equal to 18,750 minus 1100x. Okay, I'm making these numbers up, so don't don't hold me to this. What this is saying, okay, what is our slope? Our slope is negative 1100. Now, I don't know if this is true or not, okay, but the slope is a negative 1100, and that's saying when x changes by 1, x being the age of the car, so if the age of the car goes up by 1 year, we predict the value of the car to drop $1,100. Okay? That may or may not be true, but that's our prediction. Okay? This says when age of car increases by 1, we predict price y to decrease 1,100. intercept is 18,750. And that says this is our prediction for the value of a car if x is 0. So it's basically what we're predicting a new Civic would cost. Our prediction for the value of a 0-year-old Civic. Or new. Okay. Is that right? There's also something called R squared. This is the coefficient of determination. Okay. For linear regression, and notice it's a capital R squared. For linear regression, this nice property holds that big R squared is equal to the correlation value squared. Okay. For other regression, that's not the case. But for linear regression, big R squared equals little r squared. So in our last example, where r is equal to 0.8, then big R squared would equal 0.8 squared, or 0.64. Okay. R squared, big R squared tells us how much of the variation in R, the variation in Y, or the response, is explained by the linear model, or X. Okay, so it tells us how much of the variation in Y is explained by the model. Okay? And for linear regression, there's only one other variable in the model, which is x. So for linear regression, it tells us how much of the variation of y is explained by. So this also works just as well. Explained by the variation in x. So in our simple case, it tells us that 64% of the variation in y is explained by the variation in x. What does that mean? Alright, so again, I have 1, 2, 2, 6, 4, 3, 4, again, what is the what is the variation of y? The variation of y, let me just all of our data points in y are 2, 4, 6, 8. Okay, the 4 data points in y are 2, 4, 6, 8, and y bar is at 5. Okay, the variation of y just tells us, you know, basically the square distance from the mean there. We have a total variation of like 20 over 3. So the variation in y, or the variance, is equal to 6.67. You can take the square root of that and you can get 2.58 something. Okay. How much of this is just pure randomness versus how much of it can be explained by taking into account x? Okay. Well, we fit the best fit line, and we said with our model, this is what we predict y to be. Okay. The lines aren't exactly the dots aren't exactly on the line there. Okay. Versus without. So if x were not in the picture, if I told you nothing about x, your predictions for y would just be random. Would just be around 5. Okay, that's the best that you can do. But now that we've included this other bit of information x, we can kind of refine our prediction for y. Okay. I'm trying to think what a good thing would be for x and y. Okay. If I said y is the number of closets in a dwelling and x is the number of bedrooms in a dwelling, this could kind of work. Okay, so just go with me here. So we have 1 bedroom, we might have 2 closets. There might be a place with 2 bedrooms and 6 closets, okay? And there could be a place with 3 bedrooms and only 4 closets, and another place with 4 bedrooms and 8 closets. Who knows? Okay, let's just say this is my 4 data points. Okay, so if I told you nothing about how many bedrooms were in a house or a dwelling, and I just said, well, the average from our data is 5 closets, and I told you nothing, I said, oh, how many closets would you predict? Your safest guess would be 5. Okay, but now that we have this model taking into account the number of bedrooms, we can kind of refine that. Okay, I say, oh, a place has 4 bedrooms. And you can say, oh, well, I predict to have more than the average number of closets, more than 5 closets. And I tell you another place only has 1 bedroom, you'd say, oh, okay, well, it probably doesn't have as many closets. So we can see how different our predictions are for y versus the safe value of 5 and what our model tells us. Okay, so the difference here and 2, 5, and it's there and there. Okay. Well, the total sum of squares, I should have actually left this as sum of squares of y. If I do 2 minus 5, 6 minus 5, 4 minus 5, and 8 minus 5, okay, because this is 3 units away, so this distance is 2 minus 5, I have a distance of 3, and I square that, and I take this distance, and I square that, and I do that to all of these. My total sum of squares for y would equal 3 squared plus 1 squared plus 1 squared plus 3 squared, I would have a total sum of squares of 20. Okay, so that's how much variance there is between each of the data points and just the mean of the data 5. Is that okay? Just wanted to let this sink in. Versus our sum of squares residuals, which we had already calculated, and we had that to be 7.2. So the sum of squares residuals, this is the part that is still unexplained by the model. Okay, so the model says, okay, well, for a house that has 1 bedroom, we're predicting 2.6 closets. In actuality, the place only had 2 closets. So that 0.6 of a closet, which doesn't have a practical interpretation, but that 0.6 difference is our residual. That's the part that, you know, our best guess was wrong by 0.6. And over here, our best guess was wrong by 1.8, so on and so forth, okay? Our total residual was 7.2. So basically, the difference between this and this, or that ratio, this is the part that's unexplained by the model, okay? So the amount of variation unexplained by model would be 7.2, the sum of squares residuals, divided by sum of squares y, 20, which gives me 0.6. Yes?
Can you explain to the 0.6 closets again? Like, totally lost me on that one.
So when we, my predictive model was y hat is equal to 1.6x plus 1. Okay? So it says, you know, for a place with 1 bedroom, I would predict the place to have 2.6 closets. Okay? It doesn't quite make sense to say I'm predicting 2.6. You're not going to be right, because you either have 2 closets or you have 3 closets. Okay? But my best guess right now is 2.6. Just like the average number of kids is 2.3 kids per household or something. Okay? We're predicting 2.6 closets, and in reality there was 2 closets. So the difference between my prediction and the reality was 0.6. Okay? And we did the sum of squares residuals and we got 7.2. Okay? And the sum of square y, which would just be the difference between each point and the mean of y, was 20. Okay? The ratio between that and that was 0.36. This is the proportion of the variation in y that's unexplained by the model, which tells us that the proportion of the variation in y explained by the model would be 0.64. Okay? So our model tries to explain why the different y's have different values. Okay? Why does that place have 6 closets and that place has 8 closets and that place has 2? Well, we can just say, oh, all houses are different, they're going to have different amounts of closets. Okay? Or we can say, well, part of the reason why the houses have different amounts of closets is based on how many bedrooms there are. Okay? And if we take into account the number of bedrooms in the house, we can explain about 64% of just the variation in closets. Okay? But of course, all houses are different after all, and so 36% of the variation is still unexplained. So that's R squared. It's the coefficient of determination. It tells us how much of the variation in y is explained by the model, or is explained by the variation in x. I think that's it. I think that's it. So, okay. That only covers up through, like, I don't know, the first 3 sections of chapter 12. it's up to you if you want to read more of chapter 12, or you can I recommend taking a peek at section 8 of chapter 12, which talks about other regression methods. You don't have to worry about understanding fully what's happening, but just kind of be aware of the multiple regression and the logistic regression, because in your research or as you do work, you might come across a situation and you'll say, well, I don't remember ever learning about it. You probably didn't, okay? Because we're learning very introductory level stuff, okay? But at least having an awareness, you might know where to look next. Yes?
Is the amount of variation unexplained always going to be the complement of R squared, capital R squared?
Yes, yes. So this is the amount explained by the model, so 1 minus that will always be the amount unexplained by the
So
model.
what's the purpose of the calculus?
I was just illustrating, okay, because here I said we just took R, 0.8, and we squared it and we got 0.64, okay? I was trying to illustrate that it really is actually 0.64, like the amount explained by the model really is 0.64 by doing this, I don't know, maybe unnecessary explanation of how we got this 0.36, okay?
Is there a term for the value of 0.36 in this case? Or a variable?
No. I don't think there is. Maybe. I just know this is R-squared coefficient of determination. That's the 0.64, right? And so the opposite. I don't know what the opposite of that. Okay. All right. Well, we'll see you guys next week. If you have questions on anything, come.